Alright, I want to show you this thing I've made this week. There's a channel called GreatScott. He's a German guy, and he's made a lot of videos that explain in a really easy to understand way how to make a lot of different things. And it's really going to help you a lot if you're trying to get an understanding of generally how electronic devices work. This one here is supposed to be a bike alarm, so you attach it onto the seat post of a bike or similar, somewhere else on the frame, whatever, in a 3D printed box, and it detects when someone touches the bike, or not really touches, but when they shake the bike or knock it or any kind of movement beyond a certain limit is going to trigger the alarm. But in his video, he had a very small buzzer, like that big, and it was on the outside of the 3D printed case. So people were like, you can just put your finger over it and it's going to stop it from working, or if you just throw water over it, it'll break it. So I thought, that's no good. I thought, what can I do to make it better? I'm sure there were some other issues with his design as well. It wasn't obvious like how he was turning it on and off. It looked as though he had to take the whole thing apart to turn it on and off. I'm not really sure, but it just didn't. The design didn't seem so perfected, and the buzzer was so small that you wouldn't hear it in an actual street situation. You wouldn't even probably be able to hear it from very far away. So I thought, what can I do? Now, one of the issues he had was firstly, he's LiPo battery, like you'd find in a cell phone or like a portable speaker. And then he had this controller board which controls the voltage of the battery. It allows you to it acts like a BMS, I suppose. It allows you to charge it through a USB connector port here, and then he had a VCC battery out, so he had this slide switch to turn the power on and off, but there was no sort of obvious way of how he was accessing this switch from the outside of the container. But I've never used this or this, so I was like, it's also quite big. It's quite a big thing, this. And if you get this wrong, this can set on fire or explode. So you don't really want to mess about with that if you're a beginner. Do you see what I mean? What was this? Was this his? Yeah, this I think was his voltage regulator, which is this thing here. Look, this little thing here. Now, because he was using a 4 volt, it's just a single. It's like an 18650, so it goes up to 4.2 volts. It will drain down to like 3.5 or something. Or maybe less, or is it 3.0? I can't remember. So he was using this 3.3 volt regulator to lock the voltage to 3.3. So if more than 3.3 comes in, it somehow sort of discards that portion of the voltage that is excessive, so he can get a solid 3.3 volts. And I'm guessing that's might be important for his detection here, because got this amplifier circuit here, but there's a detector here that depends on a constant voltage on this pin here. So if his voltage varies, it will scale up this voltage here, but it might not scale up the voltage. Well, it won't scale this, but it might not scale up the voltage coming from this. I'm not really sure because this is supposed to multiply this by a fixed amount, which is like 34 times, depending on the ratio of the components and stuff, the resistors. So this is what he calls a differential op amp, and he's using a low power op amp that was quite hard to find, and they cost a few pounds each, I think. So I thought that's not very good, but because he wants this to run for like a long time off of this battery, and this is quite a big capacity battery, but he wants it to run for ages and ages, I guess. But this is just the detector part, so it's not going to suck that much power anyway. But so it has the sensor here, which is this thing here. Then it's sort of when this detects any sort of mechanical stress, the physics or whatever of this, it acts a bit like a bimetallic strip. Whereas a bimetallic strip sort of reacts to temperature differences, this reacts to electrical differences. It generates electricity in response to like mechanical force and energy input. So that's one thing. So I've swapped this op amp here for the LM385P, I think 358P, which is like one of the most common ones. The other one is the 741. I think that's older though. The 358P is the one I use, and that seems to work fine. So that's why I've got. Where is it? Here. It would be this thing here. 358P. And then this is a geared potentiometer. So this is a 100k potentiometer. He was using a 200k, but I didn't have a 200k. But this seems to work fine. And you want to dial this right down so that the voltage coming out of this line here, because this acts as a voltage divider. So the voltage coming out of here was about 30 millivolts, which is what 30,000th of a volt, and that's what I needed to trigger the thing to work when it comes through this. Oh no. This is a dual op amp. So there's two op amp circuits on one IC. So it has a differential op amp and a comparator circuit op amp on the same IC. So it all feeds back through there. This other chip is a 555 timer. So when the thing goes above a certain level, it's gonna it's amplified, but once it's going above a certain level, it's gonna exceed the level that's outputted by this 100k voltage divider. And when that does that, the output wire of the op amp, which is this yellow wire. So this is a binary output, so it's like 0 or VCC, I think. So it'll put out a few volts, and then what happens then is, when the level's higher, it puts out a few volts, and then it goes through this wire, goes through this resistor, And then I think I've got it. Yeah, I've got it on an LED, so I can see when there's an output from tapping the thing. I'll remove that in the final version because it uses power. But then you can see when you tap the piezo disc, it lights up the light very briefly, not very bright either. But what happens then is I've got this green wire coming from the high voltage side of the resistor that comes to this transistor, and the transistor is gating the ground voltage. So when this wire is on, when there's a voltage on this wire, like a one binary output from the comparator, you have this transistor will turn on and it will ground one of the pins on this 555 timer, which is the one that's going to turn it on. So it's in monostable mode, and that means it's going to produce a timed output. It's going to put an output of several, VCC, several volts for a fixed amount of time. It's going to be a stable output for a fixed amount of time, and that's why it's called like a 555 timer. It's the most common IC in the world. It has 3 modes. It has bistable, where it acts like a memory, like a latch sort of thing. It has monostable, where it acts as a timer. And it has bistable, where it acts as an oscillator. So there's a book here which is very, very good that I recommend to like kind of people that are just above like beginner level, and this teaches you how a lot of things work, but it's going to teach you how to use this 5.5 timer correctly, how to use it in every different mode, and how to get it, how it actually works, and how you can use it in all these different ways. So there's a bunch of 555 timers. Actually explains how it works, you see. So that's how I knew kind of what to do. But one of the things they say in that book is when you turn it on, it's usually gonna produce a pulse when you first turn it on, which isn't very good, and there's a way to suppress it stop it from doing that. But I'll show you. So turn this on to put it up to like 9 volts. Alright, something's gone wrong, because it shouldn't be on until I actually press it. Do you see what I mean? I wonder if it's because I sort of jiggled these, because these two resistors were touching. I don't know if that, but yeah, it's like I've created a loose connection or something. That's not good, is it? But it was working perfectly fine before. That's annoying. But is it the way I've got it hooked up? Yes, it's the way. I was testing something, so I've hooked it up so it's the Mosfet is always on. So we could put it there. That should do it. That should do it, right. Okay. So now we've got 9 volts, it's doing nothing. If I tap this, if I knock the table, it should turn on. Okay, no. Wow, what a piece of crap. Fuck's sake. Kind of working, but not. I don't know what it's doing. This is the thing with electronics, is they're extremely sort of sensitive. So if I like bring the voltage up slowly, it seems to work better if you sort of bring the voltage up slowly, because that allows the oscillator to sort of, I don't know, get established properly maybe. There we go, it's working normally now. So when I tap the table, it's going to start going. But if I just push, see, if I just push the table, it doesn't do anything. And that might not be what I want. So we might have to find some sort of way. I'm thinking to attach like a fishing wire to this thing here. Because if I just touch that very gently, it will do it. So if I had some sort of fishing wire or something, and I glued it to that, and then I put it to the seat, put it on the seat. So if someone tries to sit on it, it'll trigger that. You see what I mean? Now, GreatScott didn't mention anything about this sort of thing, so I'm not sure. It's possible that he had this set so that it works more sensitive. He had a 200k, so he had more resistance, more sort of fine-tuned voltage, fine-tuning to play with, and that could be it. He could have also been using like a bigger one of these that was more sensitive, but I tried to get one that looks very similar. So yeah, the 545 timer creates a pulse, and what happens is when this gets grounded, so it's pulled high through these 10k, stop it, through these 10k pull-up resistors. So the reset pin and the, I don't know, is this the trigger or is it the threshold? I don't know. This pin 2 is pulled high. Then when this transistor activates, it pulls it low, and that activates the cycle of the 555 timer. And what starts happening is this capacitor starts charging up through a resistor that I can't see right now. I think it's this one. It's going to start charging up. When it reaches 2/3 of the supply voltage, it's going to trigger a comparator inside this 555 timer. It's going to switch the latch over, and the latch is going to trigger it back to the other state it was on. So it'll disable the output line or whatever, disable the output line and turn on or off the discharge line. It'll turn on the discharge line, which is pin 7, I think, or it could be the opposite way around. I'm not sure, but that's the general idea of what it does. Now, what happens then is I've got my output line goes to a Mosfet. Now, this is not the Mosfet he used, he used a tiny SMD, which is like surface mount Mosfet that you need a microscope to actually solder onto an adapter before you can actually use it in this sort of scenario. You have an adapter board and you have to solder on, and it's a pain in the ass, but to get it to work at such a low voltage, because most MOSFETs are going to work at higher voltages above, like, let's say 5 volts. But yeah, I've rigged this up so it works. So what happens is the current the electricity comes through the positive wire. It runs through this oscillator circuit, which is driving the buzzer out of a smoke alarm. This come out of a smoke alarm, right? You can find these quite easily. So the power goes through this whole circuit and then it tries to go back, but when it does, it gets to this Mosfet, and this is either the drain or the source. I don't bloody remember. Why didn't they just use like terms that are easy to remember? I always remember though the gate is on the left, and then either one of these is the drain or the source. So yeah, it comes in through the middle, it flows through that metal oxide, a semiconductor field effect transistor, right? And then it comes, if the gate allows it to, it comes out of here, goes back to the ground line, goes back to the battery. So if this is turned off, if this gate signal is off, then the power can't get back to the battery, so it won't go through this oscillator circuit. It won't turn this siren thing on. And then these two resistors here, ignore this LED, ignore this. That's my voltage regulator. That's my LED for testing, but I don't need to know. This is 100 ohm resistor, and the diagrams online said you needed this. I don't know if you actually need it, but it was saying like there's some sort of oscillation created in the system if you don't have that. I don't know. This is a 10k pull down resistor, so you want that because you don't want your inputs to be floating, and that means like that the electrons build up on the gate, they have nowhere to go. So if you had like static electricity and you touched this or something, it could turn on this Mosfet even though the battery's like disconnected or whatever. Do you see what I mean? Like, even if this wire was disconnected, and if you had like a motor or something, it could be a problem. But so this allows these free electrons to go back to the battery. Of course, what I don't understand is how can the electrons go back in the battery? Because what I understand is that a battery only works if both terminals, like if basically the chemical reaction is occurring, so, and that can only happen if both terminals are connected to each other in some way. So that's the only way that electrons can sort of flow in and out of the battery. So how can it sort of act as a negative ground if it doesn't do that? But I think I don't think it's talking about that. I think it's acting as a ground in the sense that any chunk of metal can sort of accept extra electrons from a source that has like static electricity that has a lot of electrons. I think that's what it means. But this is the sort of thing you have to study these electrical engineering books to understand. So I've got a book I can recommend that's pretty cool. It's this book, and I've only read like 50 pages of it, but it seems really, really good. FY Hatch, I'm like showing. I tried another book and it wasn't really good. Now this book reminds me of A-level physics, A-level chemistry. It's really cool. But I started taking reishi mushroom and green tea extract and lion's mane mushroom and all this stuff to try do an antiviral sort of detoxification program for my chronic fatigue syndrome. and it kind of fucked up my brain for a while. I sort of felt feverish and disorientated. I couldn't concentrate. I couldn't do maths at all for a while. That was in sort of May, I think. So I kind of had to put this book down, but I really wanted to sort of finish this. It's 1,000 pages long though, and I only read 50 pages. This is a cool diagram. Yeah, we're stealing the book now. It's copyrighted material. That's pretty cool. It talks about how electricity actually works. There's a lot of maths, like heavy maths, that I haven't really done since like university or even A levels, which was a long time ago. I did A levels in like 2005. So this is really cool. But this is going to take a long time to read. But there's something I kind of regret about my life is I never really got to sort of professional level of ability in any sort of STEM subject. I wasn't bad at programming, but I wasn't an expert either. It's not really my fault that happened, but I don't know. I've met a lot of people, and I have had friends that were really at the top level of this sort of stuff. This is cool. Very cool. But you can pay like 20k to do a year at university, or you can just pay like, I don't know, 50 quid for this book, spend a month reading it, whatever, and you'll probably end up better at the subject than someone who just sort of follows instructions and sort of goes on Zoom videos and whatever and does their exam online and like looks on Google, asks their friend on Discord for the answers of the questions and all this shit. Band camps. Yeah, this is talking about how transistors were invented and how they work and stuff. Of course, I can't remember that, even though it was only a few months ago. And that is the problem with chronic fatigue syndrome. Every time I want to do something, I have to look it up again to refresh my memory. So everything takes like twice as long. But still, it's something interesting to do. This was cool. It's about calculating heat sinks and stuff. It's pretty cool. I got to about page 50. This was very interesting. This was about grounding of different things. Yeah, dual rail power supplies and how to ground them and stuff like that. It's pretty cool. I really need to study all that. Types of ground symbols. that's simple enough. Simple enough. But then it quickly gets into parallel resistance calculations. That's cool. Look at that. Resistors in series, resistors in parallel, designing a voltage divider, and that's quite cool, quite useful. And there's some equations you can learn there. You can write them out and put them on your wall or something, probably a good idea. So you see them all the time, over and over. Multiple load voltage divider. Oh wow, that's cool. But then, yeah, you get to like crazy, complicated maths pretty quickly. Multimeter. It shows you how like an ammeter or something works. That's so cool. Fuse. Kirchhoff's voltage laws. Look at that. Look at that. I'm scared of that. I never did A-level maths, and it's been a long time. I just did GCSE maths in a sort of comprehensive school full of like chavs that sort of disrupted all the lessons. We had like a black teacher called Mr. Sarfo, I remember. He was hilarious. But he was like, we always had like supply teachers and they would just sort of leave. We had this one guy from Australia and he was our form tutor, and like he just got a call one day and he went out for a sec and then we never saw him again. And then we had another guy who was like Paul Daniel's brother, and he was our music teacher, and he tried to actually teach us like how music theory works, and then he got like kicked out for like sexually abusing someone or something, or just like, I don't know, mishandling them, like roughing them up or something. It's bizarre. There was only a few teachers that could sort of hack it and would actually stay at the school for a long time that are actually good. Oh yeah, how the fuck do I say that? Thevenin's theorem. I don't know. Oh no. But yeah, this book is awesome. Norton's theorem, I've heard of that. Generating AC.